AP Chemsters, this is Mrs. Vanderwey for the last installment of Chapter 9's Blank Wall series. If you recall, I told you earlier that Section 9.10 will actually be done in class on Tuesday, so this is the last one. So Section 9.9 is all about the exceptions to the octet rule. We already talked about one of the exceptions, and that would be hydrogen. Hydrogen has what's called a duet. Hydrogen will never have an octet, so we already know there's something out there that not every element is going to adhere to the octet rule. Well, this section we're going to learn about some of the other ones. So the first one is an odd electron species. All right, so molecules and ions with an odd number of electrons are called free radicals. These free radicals are really important, and especially like organic chemistry, especially in the field of polymerization, where they will initiate the polymers to be created. These free radicals are searching desperately for an electron, and so they will grab them from where they can, and that's how they initiate these special reactions. So this is really an important idea in chemistry, and they do exist. So these free radicals can never achieve an octet, because of an odd number you're never going to. So let's go ahead and draw this Lewis structure for NO. The rules still apply. We're going to count up our valence electrons, we're going to place them around, and although we know we'll never achieve an octet, we still got to get as close as we can to an octet. So let's check this out. Nitrogen has 5, oxygen has 6, for a total of 11 electrons. Those are all electrons we got. All right, so here's N and O. I put 2 there. I got 9 more electrons to go. Let's go. 1, 2, all right, there's 6, 7, 8, and I'll put 9 by itself. There's nothing I can do about it. So let's check this out. Oxygen has 8. That's good. Nitrogen has, 5. Can we do better than that? The answer is yes. So what happens is, like before, we can take those 2 bottom electrons, or the top 2 if you really want, and put them between nitrogen. I know that's kind of messy because my board is that way. Let me kind of clean this up. And there we go. That would be a better looking structure. Are there 11 electrons? Let's count. Here we have 2, let me use another color. 2, 4, 6, 8, 10, 11. Yes, I have 11 electrons. There's nothing I can do about it. Oxygen has 8. Nitrogen actually has 7. That's as close as we're going to get. So this structure is pretty good. Okay. What about the next one about nitrogen dioxide? Let's count up again. So we have 5, and this time we have 2 oxygens, so we have a total of 17 electrons. Let's do this. All right, so nitrogen's in the middle, and I put the 2 electrons on either side for the oxygens. So now I've used up 4 electrons. I have 13 more to go. All right, there's 6, there's 12, there's 13. Okay. How are each oxygens doing? They each have 8. That's pretty good. Nitrogen only has 5. Well, can we do better than 5? And the answer is yes, just like the one up here. We were able to do better than 5 up there. We managed 7 by a double bond. So let's do that. Let's pick the left-hand oxygen and double bond it. So here's my double bond. So these guys swung over here. I still have those left. Still that lone pair, and that one didn't change. Now my question is, did I have to use the left-hand oxygen? The answer was no, I did not. Could I have used my right-hand oxygen? And the answer is, well, yes, you could. So we're going to do, we're going to do this. And now double bond the right-hand oxygen. And there's my left-hand oxygen. Have I used 17 electrons? Well, if you count, let's see here. 2, 4, 6, 8, 10, 12, 14, 16, 17. Yes, I have 17 electrons. I have 8 around each oxygen and 7 around the middle nitrogen. That's as good as I get. But what have I created? I have 2 valid Lewis structures. I have a resonance structure. So how do I finish this? I need a double-headed arrow between the 2 structures. Okay, that tells me it's resonant. All right, problem number 23. Which of these molecules would you expect to be a free radical? How did we define a free radical? It has an odd number of electrons. Let's count them up. Carbon has 4. Oxygen has 6. That's even. That's not it. Carbon has 4. 2 oxygens would be 12. Well, that's even. 2 nitrogens is 10 plus 6, that's 16. That's an even number. Here's 5 plus 2 times 6, that's 17. Oh, that's an odd number. That's our free radical. All right, let's try looking at the next one. Incomplete octet. Boron and beryllium can also be electron deficient. Whoa, do you see that? That says beryllium. Beryllium's a metal. What are we talking about? I thought you said that we're talking about nonmetal. Go back in, I think it was section 9.6, and we talked about electronegativity. If you look at beryllium being a second period metal, it has a pretty high, for metals that is, electronegativity. So it can have a polar covalent bond. Again, the only way to truly figure this out is to melt your solid. And if the solid, or I'm sorry, the liquid that results from the melting conducts electricity, then it truly is ionic. But if you look at these electronegative differences, and beryllium is high enough where it can have this difference between 0.9 and 2, or excuse me, 0.4 and 2.0, it can have a polar covalent bond. Okay. Well, because you already know it's special, it can also be electron deficient. Beryllium and boron don't need 8 electrons around it. Now, does that mean their chemistry is special? And the answer is yes, it's very special, okay? Boron trifluoride, like the example we're going to draw, is a reactive acid because it is seeking those electrons. All right, I'm sorry, it's an acid. It's seeking the electrons. It's electron deficient. So let's try this out. Boron has 3 electrons, and fluorine has 7, but I have 3 of those, so it looks like 24 electrons. So let's do this. Ready? So here's boron, and the rules are the same. I used up 6 by putting those bonds there. So 6 minus 24 is 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Do you remember what we did the last time we started off like that? We swung 2 electrons over and created a double bond. What's wrong with that? Can fluorine form a double bond? That's a great question. Let's go back and look at our notes. Okay, do you see where I went back? And it says rules for writing Lewis structures. It says here, if the central atom has less than an octet, then a multiple bond is necessary. The only elements that can do this is carbon, nitrogen, oxygen, and sulfur. Is there boron in there? Is there fluorine in that list? The answer is no. We cannot form a double bond between boron and fluorine. Okay, so let's go back to the problem. So we cannot form a double bond between fluorine and carbon, or excuse me, fluorine and boron. Well, fluorine and carbon neither. And so that's as good as we're going to get. So fluorine each has 8 electrons around it, but boron only has 6, and that's our Lewis structure. Now, there are cases where we can have more than 8. Okay, so let's check this out. Second period nonmetals. So we're talking about carbon, oxygen, nitrogen, will never exceed the octet rule. We're never going to have more than 8, okay? The third period and heavier, so third, fourth, fifth period nonmetals will often satisfy or exceed the octet rule. So they can have 10 or 12 electrons around the central atom only. All right, so how do we know to do this? Satisfy the octet first. If extra electrons remain, put them on elements having available d orbitals. That's why the second period nonmetals cannot do this. Carbon, you have 2s2, 2p2 as well. Is there a 2d? And the answer is no. But if you talk about third period, you're talking about 3s2, 3p6. Is there a 3d? Yeah. But when you're in that period, they're not being used, but they're available. So if you have available d orbitals in the third shell, the fourth shell, the fifth shell, there are d's available. You can exceed the octet rule. So it says, when necessary to exceed the octet rule for one of several third row elements, assume that the extra electrons are placed on the central atom. So let's do this. Let's draw the Lewis structures for the following, okay? Though here's arsenic pentafluoride. Arsenic has 5 and then 5 fluorines. Let's check this out. So we have 5 plus 5 times 7. We're talking about 40 electrons. Holy cow. Let's try this. So arsenic, all right, so we have 5 fluorines. All right, and then what? We got to make sure we have enough. So I've actually used up 10. I have 30 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I'm done. All right, each fluorine has 8 around it. Arsenic has 10. That's perfectly fine. Let's try this one. Sulfur hexafluoride. So we have 6 plus 6 times 7. That's 42. We're talking about 48 electrons. Okay, so here's sulfur, and I have to put 6 fluorines around the central atom. Holy cow. Well, by doing so, I've used up 12 of my 48 electrons. I have 36 more to go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. If you count them, I have 48 total electrons. Let's try xenon. Xenon's a noble gas. What are you talking about? Holy cow. Well, xenon has an unfilled d orbital. We can use those spaces to create bonds. So xenon has 8 and fluorine has 7. So 8 plus 14 is 22 electrons. Let's see what we do. Here's xenon, and here's fluorine, each with 2. Okay, so I've used up 4 electrons right now. So 4 minus 22 is 18. Watch. 2, 4, 6, 8, 10, 12. I still have 6 more electrons to place. So I can place them around xenon. 2, 4, 6. And I'm done. Okay, last one is xenon tetrafluoride. So I have 8 plus 4 times 7. It's 28 plus 8. We're talking about 36 electrons here. Ready? So here's xenon. And here's 2 electrons, 4, 6, 8. So I've used up 8 electrons. Looks like I still have 28 more to go. Ready? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 4 more electrons to place. All right, 2, 4. I'm done. Okay, so now we're talking about problem number 24. Which molecule can have an expanded octet? I am looking for elements that are beyond the second period. So carbon is my central atom. It's in the 2p shell. It cannot expand. Phosphorus is in the 3p shell. This can expand. Nitrogen is in the 2p shell. This cannot expand. The only one available will be the phosphoric acid. Folks, that's it. I'm sorry that this was so long and involved. I hope you've learned a lot in this chapter. Hopefully you were forced to learn some of this on your own. I do hope that these videos were helpful. On Monday, come in with questions. We'll probably be reviewing the highlights of this, what Mrs. Blankenship and I felt were important from this section. And then on Tuesday, we're going to be talking about 9.10. So we're talking about another form of calculating energy. And on Wednesday, we're going to actually start chapter 10. We're going to have a little bit quizzes down the road that will cover chapter 9. Have a happy rest of your holiday. Please don't cram on Sunday to do all this. Otherwise, you're going to be burned out of AP chemistry. See you next week. See you next year. Bye-bye.